A watched pot never boils. Your grandmother said it, and in your kitchen, she was wrong. The pot boils whether you stare at it or walk away. But shrink that pot down to a single atom, and the saying stops being a joke. Down there, watching something closely enough can keep it from changing. Not slow it down in your head, actually keep it from changing. And in 1990, a small team in Colorado set out to do exactly that, on purpose. To see why that's such a problem, look at the rule it breaks. You've trusted this rule your whole life, that looking at something only tells you what it was already doing. You glance at a clock, and the hand was already moving before you looked. Looking informs you. It doesn't reach in and change the story. In the quantum world, that rule comes apart in your hands. The name goes back to Zeno, a Greek thinker from about 2,500 years ago who loved tying common sense in knots. His favorite was an arrow. Fire an arrow across a field, then freeze it at a single instant. In that frozen moment, the arrow isn't moving. It's just somewhere. Freeze the next instant. Still not moving, just somewhere new. So if every instant shows an arrow standing perfectly still, where does the motion actually live? For 24 centuries, that was a riddle for philosophers. Then it walked into a physics lab and turned real. Here's the modern version. Take something tiny that's allowed to change. Not a ball rolling on a table, but a single ion, an atom with one electron stripped away. Picture it as a switch with two settings, state 1, state 2. Give it the right nudge of energy, and quantum mechanics says it slides from the first setting to the second. Leave it alone, and it changes. That's the ordinary story. Now the strange part. While that change is happening, you keep cutting in with one question. Are you still in state 1? Ask it once, and you barely disturb things. Ask it again and again, faster and faster, and the slide toward state 2 begins to stall. Pack the questions close enough together, and the change that was supposed to happen barely happens at all. The system sits there, pinned near where it started, held in place by nothing but the act of checking. This is the Quantum Zeno Effect. The math behind it was worked out in 1977 by two physicists, Baidyanath Misra and George Sudarshan, and what fell out of their equations was hard to accept. Measure a quantum system often enough, and you can hold its evolution still. It should feel wrong, because nothing in your day works this way. Staring at a candle doesn't save the wax. Watching a glass tip off the counter doesn't catch it in the air. So why is an atom different? Because an atom isn't a tiny machine with a hidden answer ticking away inside, waiting for you to peek. Before you measure it, it isn't quietly sitting in state 1 or state 2. It's a blend of both, a spread of possibilities still being written, and a measurement forces it to choose. To answer, right now, in plain language, 1 or 2. Every time you force that answer, you reset the story. The system starts drifting toward state 2. You measure, and it snaps back to 1. It starts drifting again. You measure, and it's back to 1. Picture it less like freezing an object in ice and more like a sentence nobody ever lets you finish. Start again. Start again. Start again. The future keeps getting cut off a half step before it arrives. And there's a clean reason this works, hidden in the timing. Right after a measurement, the chance of a quantum system slipping away from its starting state doesn't rise in a straight line. For the first sliver of time, it rises far more slowly. So if you chop the change into tiny pieces, measure, wait a blink, measure again, you keep catching the system in that slow, early window and dragging it back before it builds up speed. Slice time finely enough, and in the perfect, ideal case, the change never happens at all. For years, that lived only on paper. Then, in 1990, Wayne Itano, Daniel Heinzen, John Bollinger, and David Wineland built it for real at the National Institute of Standards and Technology in Boulder, Colorado. No mysticism. Real ions, real fields, real laser light. They took about 5,000 beryllium ions and held them inside a trap built from electric and magnetic fields, then chilled them with lasers to less than 1/4 of a degree above absolute zero, far colder than the empty space between stars. The two settings of our imaginary switch were two energy levels inside those ions. First, they placed every ion in state 1. Then, they switched on a radio wave, tuned to carry the whole crowd smoothly from state 1 over to state 2. Left to run on its own, that radio pulse would walk essentially all of them across. Then, they started interrupting. During the push, they fired in short flashes of light, and those flashes were the measurement. Not a scientist squinting at a screen, a physical interrogation. The light was tuned so that only an ion still sitting in state 1 could answer it. If the ion hadn't moved, it scattered photons and lit up. If it had already slipped toward state 2, it stayed dark. That flash asked the question, "Are you still in state 1?" And every ion had to give an answer. With no flashes, the radio wave did its job. The ions crossed over to state 2. Then they added the checks. One flash during the push, and a few ions got held back. Add more, and more stayed behind. Every time they packed in more measurements, fewer ions finished the jump. By the time the flashes were coming thick and fast, most of the ions were stuck right where they started, frozen near state 1. Not by cold, not by force, by being asked over and over whether they'd moved yet. And the numbers landed right on top of what the Quantum Zeno math had predicted. Now this is exactly where people drive off the road, so slow down with me. This is not about consciousness. The universe does not care whether a human happens to be looking. Nobody's mind reached in and pinned those ions down. The measurement was a flash of laser light, a scattered photon, information leaking out into the world around it. That's all it was. Strip away the drama, and a measurement is just physical contact with the outside. And at this scale, that contact is enough to change what comes next. A measurement isn't a window you look through, it's a hit. Which leaves the part that's genuinely hard to put down. If the act of checking can hold a change in place, then the line between a system and what's being done to it gets blurry. The question becomes part of the experiment. The answer depends on how hard and how often you ask. That's the real paradox, and it's not the cheap version where minds conjure reality out of thin air. It's quieter than that. A quantum system left alone is free to drift, to flip, to decay, to spread across everything it could become. The same system, interrogated hard enough, can be held right where it began. It's almost as if the future needs a little privacy to happen. So your grandmother was wrong about the pot. Stare at it all you like. It boils right on time. But the atom plays by another set of rules. And the more carefully those scientists learn to ask, "Are you still there? Are you still there?" the more the ions answered the only way they could. Yes, yes, yes. Until the change they were supposed to make almost disappeared. There are a few books in the description if you want to go deeper into the kind of physics we explore on this channel. And if you want to keep going right now, there are 2 videos on the end screen that connect with the bigger questions we keep coming back to here. Thanks for watching. See you in the next one.